Okay, good afternoon to all of you. Uh, I think you have attended 5 sessions. This is the sixth session which I'm going to deliver. My topic is clustering for IoT data. So I'll be discussing about uh, starting from what is data and then what are the characteristics of data and then how this clustering actually plays an important role for analysis. So that is my uh, flow of the talk. Let me first talk about, I think in the first talk, which Dr. Vishal has delivered, he has introduced IoT and smart cities. Okay. So what is IoT is? IoT is a combination of embedded technologies, including wired and wireless communication, sensors, actuator devices, and the physical objects connected to the internet. So it is basically, if you look on IoT structure or IoT architecture, then it is a three-layered architecture. And at the lowest level, there is physical devices. It could be anything. It could be sensors, it could be computers, it could be a mainframe, it could be any smart house or smart buildings, could like devices or nodes could be anything. And then data sensed and then forwarded. Then there is a middleware which actually take care of data pre-processing, data maybe you can say noise removal and everything. And then it actually creates data for the cloud, or you can also store on any sort of server which is actually placed at any official or institutional premises. So that data comes to there, and further you can use it for your decision making. So this is what IoT talks about. The purpose of Internet of Things is to develop a smarter environment and a simplified lifestyle by saving time, energy, and money. So when we say that we look for smart homes, when we look for smart city, when we look for smart country and all, then what I'm looking for is that environment should be smart enough, which actually provide you a lifestyle which actually can be provided with minimum time span and minimum energy consumed, and also it should cost you less. So that is what we look for. There are four main components, like we call it sensors. It can be computers also, laptop also, it can be a building, it can be a LAN or WAN, anything could be at the physical level. Then you have a processing network, which is responsible for data sensing, data sending, and obviously it could be one hop or multi-hop sort of communication may be there, depending upon what networks you have. Then you look for data analysis, where what we look for is that you have data, now you look for informations or knowledge out of it. In data analysis part, you can do what you can do is you can apply mining algorithms, say association mining, classification, predictions, clustering, machine learning algorithms, which actually also part of data mining algorithms, and infer sort of knowledge which can be used for decision making. That is what data analysis part is there. Obviously, when we talk about IoT, it is actually a monitoring system. Whether I think, say, for example, if you look for wildlife monitoring system, then it can be building monitoring system, it can be battlefield monitoring system. So, system is actually developed for monitoring. It is actually producing data, maybe per second, per minute, or whatever time period or time intervals you can fix. So it is actually producing a huge amount of data for you. And then you can look for analysis and other things. I'm just giving you, I've just collected this data from one paper. There are some use cases. You can see that starting from what you look for is smart traffic, smart health, smart environment, weather predictions, smart citizen also you look for, smart agriculture, smart home, smart citizen. That means basically weather prediction, then agriculture, there is air controlling also, there is public place monitoring, then human activity control. Just go through it, you'll find that what sort of data is actually involved in this process is that either you have a stream data or maybe a huge data, which could be stored in cloud or in terms of big data in servers. And there are few cases where actually there is data, and also there are some data which is historical data, which is that means we are looking for some data warehouse sort of things. And where you are processing these data is actually either you go for edge or you can go for cloud. Now the question is I think I remember that in very first lecture, one of you have asked what is the difference between cloud and edge, or I think rather you have asked what is difference between IoT and edge and all. So if I go for it, then what is happening out there is, let me just you can see that when we it is actually this sort of thing where actually you have sorry you have three layers of thing. This is where actually your cloud is there, this is your edge, and this is your physical. Yeah, that means devices are kept in the lower level where actually that has a sensing and all. This edge computing is actually, you can see that this can be referred as that you are just fixing some of the servers in between cloud and the sensing environment. Reason is that just to improve the degree of availability in terms of data and processing. Okay, so what we are doing is that there are some partial data analysis or data processing you can do out here. So you can do like you can have multiple servers at this place where actually each servers may dedicated to a specific services and all, and then certainly the same data can be forwarded to the cloud. So edge computing is something which is coined in terms of that while these networks where actually you're looking, say for example wireless sensor network, if you look for, it could be at any places which may be like you may use it for disaster management, you may use it for seismic reason, you may use for military battlefield monitoring and all. So what you look for, these edge computing can be done near to this battlefield or whatever near to places, which that means the availability of the data to this particular label is high, and then you can push the data afterward to the cloud. So that is what difference is. Uh,
So where we can put the fog.
okay, so now then we go for this what we call it as smart data characteristics. Sometimes I become very much conservative also, because since everybody is using it, that I think data characteristics itself is smart enough, but still I'm using it as smart data characteristics. So in smart data characteristics, if you look for IoT data, then you have big data. Then where actually you look for volume, variety, velocity. I think this part is already covered. A little bit introduction has been given. I'll be also giving some of the introduction on this. Some examples I'll put where so that you can understand. Even I'll add on some of the characteristics in big data terms. Then you look for data quality, redundancy, accuracy, dynamicity, and granularity. I think redundancy is very much familiar words. It is repetition of data. So always we look for whether it is any sort of data bases, data warehouse, big data, or if you consider it, we always assume that we should go for such system where actually the redundancy should be minimum, because actually that high redundancy always create problem in terms of consistency and all. Then uh, accuracy is always like I think most of us are actually doing so much work on data. So we look for how accurate a particular algorithm is, how accurate. In this case, what we are looking for is that how accurate the data is. That means the data is sensed, and with reference of the environment, that whether the data represents the object which you are referring. So it should reflect the correct data for with reference to the environment. Dynamicity is when that means that the data which is coming dynamically. That means, say, for example, data stream where data is coming in intervals, maybe in seconds, minutes, and all. So every time this data is coming, you have to update your data. That means whether it is on data is on kept on edge or whether it is data is kept on cloud. I think whenever data comes, you have to update your previous data so that new data can be a part of the data also. Granularity is something which is very important. Granularity means that what you are looking for is that uh, say you have some database, then I can have, say, within this there are, you can say, I can have department 1, then I can have department 2, then these departments will have several files, say file 1, file 2. Similarly, this has file 3, file 4, then file 5. Similarly, all these files are records, say R1, R2, R3, and all. And similarly for these all. And obviously, even records also can be seen in granular way, where actually you can see that the records are actually having multiple attributes. And then some atomic data, which is actually each of the attributes is having. So it is basically this from top to bottom. When you see this, actually talks about granularity of the data. That means the data should be available to the user in a way that whenever required, I can go at any level of this granularity. That means I may be interested to have a single attribute, so I'll go for single attribute rather than going for the entire data. If I'm interested to have a particular file, I'll go for that particular file also. So when you look for, when you go or when you scan this from top to bottom, bottom to up, then it is actually referred as coarse granularity and fine granularity and all. And it is very important whenever you look for data analysis. Okay, so that is what I'm looking for. And then you can see that we have uh, then data uses uh, is actually semantic, completeness, and noiseless. Uh, Semantic refers that how the data actually grows and how data actually uh, provides the characteristics for the environment. And the completeness means it is actually you can actually the measure of completeness is how what is the degree of noise in the data. So the lower the noise, higher the completeness, higher the noise, lower the completeness. And always we look for noiseless data for any environment for better analysis. Now, these are actually, you can see that algorithms which is widely used in different uh, domain, uh, starting from K nearest neighbor, then naive based, SVM, linear regression, then classification, random forest, K means, DB scan, PCA, CCA, and there are some algorithms which is based on ANN and all. So all these algorithms which actually talks about what namely our uh, classification and clustering, these are widely used. Only the thing is that based on the data characteristics, based on the feature you have in the data, you have to have some decision making that which algorithm would be best for me. That is very important, very much important. Okay. So that is what we are looking for. I'll be covering the clustering part, whereas the classification algorithms will be covered in machine learning algorithms. Okay, I think you have gone through this probability and statistics lecture, then you have gone through this linear algebra, vectors and matrices and all. You'll find that while going for classification and clustering, these all concepts are very useful. Say, for example, like you can see what I sorry you can actually visualize that in classifications you have decision tree algorithms, say ID3, then CART, then C4.5, which actually make use of entropy, then uh, gain ratio, then Gini index and all. All these formulas are actually derived from probability and statistics. And then there are some like I think Dr. Vishal has talked about some inference in wireless sensor network, where actually he has used matrix, where actually through matrix manipulations he is actually trying to take some inference out of it. All this matrix manipulation is required. Even in case of almost all the clustering algorithms, we make use of matrices where actually we convert the matrices into dissimilarity matrix or similarity matrix, and then we make use of several distances which is available to us depending upon domain and environment, and then we move forward to apply the algorithms accordingly, because these are the preliminaries of these algorithms. So these are very useful for data analysis, so that I can connect. Just giving idea about what are the IoT data issues and challenges. Certainly, we handle high volume, fast velocity, and different variety of data. We look for data abstraction and then categories of IoT application as per unique attribute and features. Data privacy issues is also a one concern. And the most important part is the selection of algorithm. It is very much important that which algorithm or which category of algorithms or what category of algorithms you are actually taking for your application. So it may be the case in normal cases, what we do is actually we take 2, 3 different category of algorithms. Say I can take one machine learning algorithms, I can take some statistics based algorithm, or say I can take some algorithms which may be in non-machine learning based and all, and then I can compare all these algorithms and I'll see that which one performs better than others. And if I get a good results, then I can conclude and I can go for the best algorithm out of it. So that part is actually what we are doing day to day and for all our research works. Data abstraction is very important, because what we look for is that how the data is actually It is data is coming from the lower level. It is sensed, or it may be coming in a in form of a raw data and all. Then you have to infer information out of it. So abstraction says that when you actually convert the data into a readable form, or it converting data where actually characteristics are there, then abstraction actually applies, it gives you the flexibility, then you can reduce the number of characteristics of the data, provided that the reduced number of characteristics of the data still give you a best knowledge of the environment. So that also we look for. So that those are the issues. It is actually, these are the important actually issues of the IoT data and all. I'm just switching to the some sort of big data paradigm. I'm just giving you some examples. Actually, you have just gone through it in a previous lecture, so I'm not going to define it. What I'm going to do is that I'll give you an example where actually you can visualize what is happening in the environment. Like if you go for velocity, it says that the how fast data is coming. That means data rate is very high in the system. Just now, just I think 1 hour before, I have collected these informations, and you can see that almost 3.8. I think I'm wrong. It is 3.8 billion queries per minute on Google are performed. Okay, so and then around 20 plus million photos per minute are viewed. Then every minute we upload 300 hours of video on YouTube. Every minute, over 293 billion emails are sent and received daily. And as far as tweets are concerned, you can see that there are 350,000 tweets are sent in a minute. So see how much data actually we are producing in the environment. And all these data need to be analyzed. So the moment we say analyze, that means data science comes in between. And all these algorithms, machine learning, deep learning, data mining, all plays an important role for analyzing these sort of data. And this is not a small amount of data, it is a huge amount of data. I think this is the first point is it is actually 3.8 million queries per minute, I hope. So what we are saying is the amount of data generated every second we look for. Obviously, data is generated by machine, network, human interaction, like systems like social media also. So all these massive data is generated. The another example which is very important and this is actually related with IoT, that I think all of us are aware of Airbus, which is actually a company which produces aircraft, helicopters, and others. So if you look for one flight of Airbus, it generates 10 terabytes every 30 minutes. And if you look for one flight data generation, it is actually generating 640 terabytes of data for you. So massive data it is generating. Just imagine that if the same flight is going for multiple flights per day, how much data it is generating for the environment. Okay. Even some examples like self-driving cars will generate 2 petabytes of data every year. Then from now on, the amount of data in the world will double every 2 years. So by the end of 2020, we'll have 50 times the amount of data as that we had in 2011. So just visualize the integration of the data. Variety, uh, that means different types of data we can now use. That means you're talking about data which is in terms of numerical values, which may be an image, which may be a video, which may be emails, which may be audio also. So, so the system has to include all such data so that all can be a part of your analysis also. So that is what we're looking for. Then we look for some other characteristics of the data, which is also referred as value. Uh, what we are saying, that having access to big data is no good unless we can turn it into value. Say, like, companies are working on it, discovering a consumer preference or sentiment, making a relevant offer by location. Say, you can actually offer customers based on location. Say, there are preferences in North India, there are preferences in South India, there are preferences in West and East also, like in terms of food habits also. So if you look for pantaloons, big bazaar, and such type of retail markets, then certainly they can actually analyze the data in terms of location and certainly offer may be given with the location priority, because uh, the taste and the likings are different when you move from one location to another location. That is also important. Veracity is one thing which actually it actually gives you the question, are the results meaningful for the given problem space? It's about data quality and understandability. So it is basically very much important when you have automated decision making, where that means no human is involved. So you have to have a surety that both the data and analysis are correct. So that is what veracity talk about. Variability is very interesting thing. Say, like, if you look on example, then what is saying is that suppose actually you are actually visiting a bakery, say for consecutive 10 days. So bakery actually sells 10 different breads. That is variety. Okay. So 10 different breads are available. So that actually refers variety. But just imagine that you go to the bakery 3 days in a row, and every day you buy the same type of bread, but each day it tastes and smells different. Actually, that is what variability is. So it may be the possibility, or it may be that your whatever data your environment is sensing, it may be the case that with a different time zone, or maybe based on spatial and temporal uh, characteristics, it may give you different sort of data. So that is what we look for. Okay. Visualizations that will be covered tomorrow by Dr. Ramesh will be I think giving you the hands-on sort of thing on Tableau visualization tool. Uh, Tableau is uh, actually not open source. So certainly he will give you the idea from his system, and certainly you can go for using it for your offices or for your research work. Visualization is actually a complex graph that can include many variables of data while still remaining understandability and readability. So it actually, whether it is graph, histogram, or pie chart, or anything which can actually include multiple variables at a time and can reflect the knowledge out of it. So data generating points, it can be smartphones, IoT, emails, blogs, Google, YouTube. There are so many sources, etc. I'm just giving you two slides for what we look for is like where actually when you have a huge data and big data, then there is a possibility that you may not handle the data with a single storage and all, or you cannot handle it at one go for an algorithm. So there may be a possibility that you may go for parallel processing. In that case, this MapReduce and SDFS is very useful. Uh, you can see that HDFS says that actually you can, there is a name node which is actually coordinator, and it is connected with all the slave nodes. The individual systems are there. Okay. So these are the systems. Let me go for. So what we are doing is that, oh, sorry. Okay. So what we are having is that you can see that these are slaves, and these slaves are actually storing the data, or data is distributed over these slaves, and each of these slaves can execute data, the algorithm parallelly. It can be done through MapReduce framework also, where actually each of the mappers will be in the each of the slaves, or you can say terminals, and it can process the data locally, whatever data locally available, and implement or execute the algorithms. And then there is a reducer component which actually combines the results of all the mappers, and it gives you as output and all. This is simplest architectures we have, which where actually mapper reducer works. Uh, if you can see this, this is actually you can see that the top part is Spark, whereas below talks about SDFS. In Spark, actually, it is a in-memory computation is involved, whereas Hadoop, we are doing a disk-based processing. So difference you can easily see that in case of Spark, everything is done on memory based, whereas in case of Hadoop, it is done on disk based. So obviously, in case of Spark, it processes it faster than what is the Hadoop can do that. Obviously, the file system, the Spark is also using the same HDFS. The difference, if you look for, then Spark is actually 100 times faster in memory and 10 times faster on disk also. It can be used to sort 100 terabytes of data in 3 times faster than Hadoop of 1/10 of the machine, on 1/10 of the machines. Whereas Spark is faster for machine learning operation. Like suppose if you use naive Bayes, k-means and all, you'll find that it is faster than Hadoop MapReduce framework. Only the thing is that the moment data size becomes huge and huge, then Spark may not be a good choice in that case. So for huge amount of data processing, still the MapReduce is good choice. But for a smaller amount, I'm not talking about megabytes and all. The smaller amount of data, I mean that it may be terabytes or petabytes sort of things. If it goes beyond that, still the MapReduce framework is more feasible. Now, with giving all these backgrounds regarding what is IoT, then what is IoT data, then what is big data, how parallel processing could be done and all. I'm just moving to the main topic, which is what we call it as data clustering, in which I'll be talking about some of the, first of all, I'll talk about some data types very specific to be used for clustering. And then I'll be moving to some of the algorithms, which is very much widely used. Okay. Data clustering is actually a mining technique that divides group of abstract objects into classes of similar objects. Very simple. This is unsupervised learning, whereas if you look for classification, it is supervised. So we can see that the unsupervised partitioning of data set D into set of classes, say C1 to Cn, in such a way that data are grouped together based on a certain similarity measures, and that is referred as data clustering. See, when I say similarity measures, that could be anything. That could be distance also, that could be individual value difference also. So depending upon domain and environment, we can use these measures. I'll talk about some of them. Difference is very well known, classifications versus clustering. Classification is actually a supervised learning, whereas clustering is referred as unsupervised learning. The reason is that in for classification, data should have labels. That means classes must be known. Whereas in case of clustering, it is not necessary that we should know about the classes. It actually automatically, based on the features, it clusters. So I'll be just giving you some sort of introduction to data types. What we look for is that just you have finished uh, Dr. Satakshi has given you the platform for what how this actually vectors and matrices, what it looks like, and how what manipulation you can do go for, and how it can be used for data analysis. So this is one part of that. This is matrix. This is data matrix, which is actually object by variable structure. Okay, so it is actually representing n objects with p variables. So a relational table of n by p matrix. So once you have this particular data matrix, then you can generate your dissimilarity matrix out of it. When the moment I say dissimilarity matrix, then it becomes object by object structure. Why I'm saying object by object structure? That means, like, suppose if I'm saying that this is actually, if you look for the matrices, then let me see that whether I can help some sort of using this. Okay, so uh, you can see that what is happening out here is that this can be, say, I can say these are cities. So it can be city 1, city 2, city 3, and so on, city n. So when you have this is city 1 and cn. So this actually, these values is actually giving you uh, the information that how, what is the dissimilarity between these two. So obviously from C1 to C1 always will be 0. So all the diagonal element always going to 0 or approaching to 0. Whereas others, D21 is actually talking about how far or how, what is the distance between this C1 and C2. So this is very much useful, and it cannot, it is not only this. When we talk about that, we talk about in terms of kilometer of between the cities and all. It can be talked about for any term. Like it can, this particular dissimilarity matrix may be generated for any type of data, say maybe numerical data and as well as categorical data. Only the thing is you have to convert categorical data into some using some transformation. So that can be used. Okay, so this is what we can do. So the problem is, how can we assess dissimilarity? So there are ways of doing it. There are specific types of data which can be used for clustering, say interval scale variables, binary variables, and then we have nominal, ordinal, and ratio variables also available, or variable of mixed types. So I'll be just going in a brief that when you look for interval scale variables, then it is actually talking about continuous measurements on a roughly linear scale, say weight, height, latitude, longitude, and all temperature you look for. This is very important when, since we all are, this is very important that when we go for smaller unit, then it provides you larger variable range. And if you go for larger, then it will be giving you the smaller variable range. So it has an effect on clustering structure also. Say what I mean to say is, like if I go for, say, for example, you can see we are talking about a basketball player. So I can go for the weight of the player and I can go for height of the player also. So it always depends that what unit you are using. Say if I'll be using kgs, then somebody say I'll be using grams also. Okay, for height I you can use feet also, inch also, and even centimeter also. So just visualize that when the moment I change the unit, then the what difference of the two players actually vary. That means if in terms of fit, the two players might be very close, but the moment I switch to inch, it becomes the gap becomes larger. And if I'm going to in centimeters, it again becomes larger. So it actually gives you such sort of range. So it has effect on clustering structure. So wisely it need to be decided also. Okay. Next is, so what we use is that we make use of mean absolute deviation. The formula is this, where actually these are measurements, xi's are measurements, and mf is actually mean of the measurements. Then we go for z score for standard. standardized measurements, and this is the formula. Here you can actually observe that instead of using the standard deviation, we are using absolute deviation. Reason is very much simple, that you know that in standard deviation we make use of squared terms, and that actually is creating some sort of problems. So using this absolute deviation, the Z score can actually the outliers do not become too small, and so they remain detectable in that case. Okay. Uh, these are the distances actually you have already covered in the first lecture today. That is, I think probably you have gone through the norms. So this is same thing I'm giving you, that you start with the norms, then you go for Manhattan distance, which is actually putting q equals to 1, then putting q equals to 2, then it becomes Euclidean distance. And then there is very important one is weighted distance. Just now, I just told you that I can make use of, say, if you go for say 2, then obviously this becomes Euclidean distance. What I mean is weighted differences, that suppose these are the features of the players. Say you can say this is weight, this is height, and these are similarly. Now what I want is that for a basketball player, height is most important. So what I can do is I can prefix some weight out here, which which is higher than other weights of other features. So what will happen is, during my analysis, this height has more impact on the analysis rather compared to other features. So that is what is very important, and that helps you also. Okay. So then we move to the properties are well known to all. Then this is also one important binary variables which can be used. Obviously, when I say binary variables, then I'm talking about two values, either 0 or 1. Then there are variables which is symmetric and asymmetric in nature. When I say symmetric, that means absence of one lead to the other, whereas asymmetric, that means absence of one may not lead to the other. That means if I say not male, does not mean it is female. If I say not female, does not mean to male. If such variables I am using, then certainly it is asymmetric in nature. If I say that not male refers to female, that means it is symmetric in nature. So that I'm talking about. So actually, you can see that we make use of Jaccard coefficient for defining the distance between two object I and j, and these can be defined by b plus c by a plus b plus c plus d, and if it in case of asymmetric, it is b plus c by a plus b plus c. What is a b c d? You can always refer from this top matrix. You can see table, you can see where actually a refers 1 1, whereas b refers 1 0, c refers 0 1, and d refers 0 0. So for example, if I go for this particular data, where actually I'm looking for, say, 3 patients, we have Jack, Mary, and Jim, and then there are gender, fever, cough, test 2, test 3, test 4, like that. So what I'm saying is that gender is a symmetric attribute, whereas rest are asymmetric in nature. So I'm just putting values for y and p1, and whereas we are putting 0 for this. Now, if you see the first formula, then it is actually giving what is the difference, what is dissimilarity between Jack and Mary. So that actually is, say, Jack and Mary is this. So you can see that this is 1 1, this is 0 0, this is again 1 1, this is 0 0, this is 0 1, and this is 0 0. So if you refer the previous table, then certainly you can see that this is nothing but this is b plus c and a plus b plus c. So b is actually, you can see that 1 0. So 1 0 instances is 0 instances is there. Then if you go for c, c refers to 0 1, and it is actually 0 1. You can see that there are one instance, so it is giving 1, whereas a refers to 1 1. There are two instances, 1 1 is there. So we have 2 plus 0 plus 1, and it is giving 0.33. So Jack and Mary has the difference of, you can say, 0.33. So it is giving the value. And similarly, you can go for Jack, Jim, Mary, and all. So what I mean is that any data can be transformed in a way to be used in the clustering. Then there is nominal variables, where actually it is actually a generalization of boundary variables. Say you have color, we are using colors, and say you have red, yellow, blue, green colors are there. So instead of having two states, you have multiple states of the attributes. Then there are two way of doing it, that differences could be defined by number of matches and total number of variables, that is p minus m by p. Whereas other method is best is that what we do is that each of the states could be referred as boundary variable. Say if I can, what I can do is I can go for red, and I say either red yes or no, or say yellow yes or no. So this is y red, y yes and red no. This is y yellow yes and yellow no. So individual states could be represented by boundary variables, and then further it can be boundary variable structures can be used to feed in the algorithm. Okay. Next is ordinal variables, where actually we make use of rank. You have already done in the first lecture today by Dr. Satachi. It is actually this can be used like when you talk about any academic institutions or any industry. There is a hierarchy, say from director, then professor, then associate professor, then assistant professor, and all. So there is hierarchy, and obviously it will need to be maintained as well. So what we do is, in that case, we actually make use of this rank. So I can give, say I can say that okay, the top director can be given 4, then professor can be given 3, associate can be given 2 and 1 and all. So this rank, or certainly data types, data can be represented in the form of matrix. It can, and you can go for rank to be determined, and then further it can be standardized also using Z score and all. Only the thing is, in place of mean, you'll be using ranks. So that is also, and obviously dissimilarity can be defined as interval scale variables also. So conversion is possible. Similarly, ratio scale variables, where actually exponential scale is available, then obviously we make use of logarithmic transformations, say y equals to log x sort of things, and then treat them as continuous ordinal variables and treat their rank as interval scale, and then make use of distance calculations defined in those variables. Okay. You can also make use of mixed type of variables also, where actually you can say that the data is there, and where actually a set of attributes could be transformed into, say, in ratio scale, there are set of attributes could be transformed into interval scale, and then the whole set of this mixed sort of data can be referred, and a distance can be calculated. There is formula for that, and then it can be used for algorithm. So that sort of data types are reused for clustering. Next, what this is, I'm just giving you what actually the whole paradigm of clustering is there. You have different category of algorithms, say hierarchical partitioning, grid based, then clustering algorithms used in machine learning, then algorithms in high dimensional data also. And similarly, you can see that you have algorithms like k-means, then they have algorithms like density based algorithms like dbscan and cure, and there are hierarchical methods algorithm which is agglomerative and divisive in nature, and similarly subspace and co-clustering techniques are available also. So there are hundreds of algorithm available, like if you look from one to others, and obviously it is very hard to select the best algorithm out of it for your domain. So it's an issue for any data analyst. Okay, this is something which I can see. What is happening out here is you can see that if I'll go for so what I'm saying is that you have clusters like this, and obviously there are certain points, certain points, certain points, and obviously you know that clustering means there is you maximize the distance between the clusters, and you just minimize and you maximize. So minimize the inter-cluster points distance and maximize the intra-cluster point distance and maximize the inter-cluster distance. So to analyze the distance between the clusters, these are the formula you can use. That you can use minimum distance like the first one, and then maximum distance, then mean distance, and average distance. I think max and mean is very much clear, that each point, the distance between the points to the corresponding points of the other clusters will be calculated, and then minimum of it will be selected as distance between the clusters. Whereas maximum distance of between the clusters could be referred as the second formula gives you that corresponding each point will be distance will be calculated with each point of the other cluster, and the maximum will be the mean distance and average distance looks very similar, but it is different. What I mean is the mean distance says that we take the mean of the all the points in the cluster, and then the mean of other cluster also, and then we look for the distance between these two means. But whereas average distance is actually what we look for is that we are going for distance between each point to each point of the corresponding clusters, and then we are taking the average of that point. So that gives you the average distance between clusters. Now, this is the first algorithm which I'm going for. Is very important and very popular also. What do we call it as k-means? Uh, Process is very simple. That means randomly just choose k points as centroids. So that means suppose the moment I say that you'll go for k means clustering, then suppose you look for three clusters. So k becomes 3 for you. Now obviously points are like p1, p2, and pn. So k equals to 3 when you fix this is user defined, and obviously all the point should be mapped to these three clusters. That is what k-means does. And obviously it make use of distance, because the distance, the distance between the points decides that whether it will fall in first cluster. So this is C1, this is C2, and this is C3. That is what k-means is. This is one example which could be, you can say that it can be an example of IoT data also. What we have, that we have two attributes, say A and B, and data is there. So we start with the assumption that, okay, fine, we look for two clusters, say, and I'm referring as randomly, I've selected 1 and 4. And then based on distance calculations, these clusters will evolve. So you can see that uh, after one first iteration, it is giving you cluster 1 is having 1, 2, 3, and cluster 2 is having 4, 5, 6, 7. Now, in the next iteration, before going for next iteration, what we do is that we have to change the mean of the clusters. Now, based on the points, say 1, 2, 3, the mean vector will change. And based on the 4, 5, 6, 7, the mean of the second cluster will also change. Actually, I'm referring this. I'm referring this, and this. Okay. So this will change. And now based on like referring this, now I'll be going for checking the distance of all the points with reference to this mean now. And the minimum will win and will fall in the same cluster. So what we found is after the next iteration, the cluster 1 is having just 1 and 2, whereas cluster 2 is having 3, 4, 5, 6, 7. and the mean vector is coming as this now. Now, if you go for next iteration, then you'll find that there is no change. The moment in two consecutive iteration, there is no change, stop. And whatever clusters you are getting is the final clusters, and which will be which can be used for your decision making. So this is what K-means talks about. The problem with before going for parallel, I'll be going for saying what is the problem with K-means is that K-means cannot handle the noisy data or say outliers. Reason is very simple. Uh, Reason is that the moment if you say that there are some values of the data you have, say all the values are actually falling in between 1 to 100, but there is one value which is above 150. But since 150 above, say 160 sort of, say value is 160. Now all the values are below 100 and one value is above 160. So one cluster always be biased towards 160. So in that case, what will happen is that the one mean is actually converging towards the noise. So that becomes a problem in case of K means. Obviously, as far as complexity is concerned, it is TKN. K is number of clusters, N is number of data, T is number of iteration. Okay. Now, uh, if I go for parallel K means, then how would I see that? See, whether you go for Spark or whether you go for MapReduce, then what will happen is that you will distribute the data into different machine, or it may be in different cores as well. So say there are partitions of data D, which is D1, D2, Dn. And now each of these systems locally will actually execute the k-means. So it will go for it. And then obviously the centroids will be transferred to reducer. And then obviously the reducer has the responsibility to merge the centroids so that global centroids can be generated and can be used for further iteration. Here, be careful that it is very obvious that each of these mappers will generate different set of centroids. But the moment your iteration completes, if all the different systems will generate different sort of centroids, then it is very hard to merge the clusters. So what we do is that at every iteration, what we do is that we actually generate a global centroids, and that global centroids will be transferred to each of the mappers, so that in the next iteration, each of the mappers will actually work on the same set of centroids. Certainly, it may be noted that in the next iteration also, all the mappers may generate different set of centroids. So for each iteration, the global centroid generation will be there for the uniformity, and then the same set of global centroids will be sent back to the mappers, and the iteration will go on till two consecutive iterations of each of the mappers having the same set of clusters formation. Once it is over, then obviously uh, reducer has actually the responsibility of global centroids. So all the mappers centroids are very much same. So depending upon global centroids, certainly what we do is that all the like same centroid values, the clusters of the different mappers will be merged and it will give you the global clusters. So that is what happening in case of parallel processing, and it can be done. And it is very efficient to handle the large amount of data, and k-means can be used as well. So this is what, then there are variations of k-means and there is partition around medioids. There are two algorithms which is actually partition around medioids is used based on the cost calculations, which is actually having a bit of advantage over k-means. So it can handle a bit of noise also. Clara is something which is actually works on samples. Uh, so what we do is that instead of performing or executing the algorithms on a entire data set, we perform the same thing on multiple samples, say 2 samples, 3 samples out of data. Only the thing is, the strength is that it can deal larger data, and weaknesses is that it depends on sample size also and the sample quality also. So, but if sample is actually is biased, then certainly it creates problem. Okay, fine. So that is what we. Then there are another variations of k-means and PAM is a Clarence, where actually a clustering algorithm based on randomized search. Uh, in this case, what is happening is that samples are actually extracted within the neighbors. That means one sample you have extracted, the another sample dynamically can be extracted from the neighbor point also. And the same way the parallel algorithms can be executed on samples, and the clusters can be formed. That is what we do it. It is more efficient and scalable if you look for PAM and Clara and all. Next category of algorithms is hierarchical clustering, which actually talks about agglomerative and divisive sort of. If you this is PQRST is actually data points. So if you come from top to bottom, and then if you go from bottom to top, then it is actually when you go for top to bottom is divisive algorithm, whereas bottom to top is actually a agglomerative algorithm. So what I mean is that the entire data set D is one cluster for me, and then based on the distance calculation and the near objects can be clustered, and this can actually generate 2 clusters. Then further it can generate another set of clusters, then it can generate another set of clusters, and finally each of the data points can actually represent a cluster. So from top to bottom and bottom to top is actually giving you clusters. How then the question is, how would I extract the clusters? The extraction is very simple. But see, I just draw a line here. So if I draw a line here, then certainly there are 2 intersection points. Is this and this. So we have one cluster is this and another cluster is this. Okay, this is what we do. If I draw a line here, then certainly you can see there are 1, 2, 3, 4. There are 4 intersections, so we can get 4 cluster out of it. So depending upon your requirement, you can go for number of clusters to be there. Algorithms like single link, then minimum spanning tree single link, complete link, and average link is very much famous algorithm in hierarchical algorithms. It makes use of a concept of dendrograms. This particular figure is actually a dendrograms. This A, B, C, D, E, F is an individual data points, and based on similarity measures, that A, B comes together, then C, D comes together, then C, D comes together to E, then similarly A, B comes together to C, D, E, and then move forward, and it is actually giving you hierarchy of the clusters. This is one example of single link where actually you can see that this is a dissimilarity matrix you have. Then for single link, what we do is that first of all, we go for, uh, let me, first of all, just choose the minimum distance. This refers 1 and 2. So what we do is the first cluster will be formed with 1 and 2. Now, the question is that when you go for improved matrix, then these 2 columns must be merged for the improved matrix. So how it is merged is actually based on this, the minimum distance of these two, and these two. So this becomes this. Next iteration, see which one is minimum. So this is the minimum 3. So now 1, 2 will be merged with 3. So it can be like this, and similarly the same way you can move forward and you will get the this particular dendrograms. and putting line you can get. Like I'm saying that if I draw a line here, I'll get 2 clusters. If I draw a line here, I'll get 3 clusters. So this is what we have. Now complete link is that in case of what we are doing is that the same way I'll move, the minimum will first will be considered. Only the thing is when we merge the columns, it will be merged in place of minimum, it will be maximum. So the maximum will be considered for the improved matrix. And similarly, you can move forward and you will be getting dendrograms. Similarly, put a line on that, intersections will give you the clusters. So, and what is average? Average is that instead of going for the minimum or a maximum, you go for average of these two. So 6 plus 3 is 9, 9 by 2 is 4.5, and then move forward. In this case, you can see that in previous two cases, this was maximum minimum, this place value was maximum, but now this becomes sorry, minimum. So so what is happening is that such clusters will be formed. The problem with dendrogram and that it cannot handle a large data. Reason is very simple that when this dendrograms become when you look for the dendrograms for the large set of data, then it creates problem. But the visibility is very the problem, and extraction of the cluster becomes difficult. So certainly we have to have some sort of large data clustering algorithm. So we have large clustering for large data. We have algorithms like Birch, DVScan, and Cure. These are very important algorithms which widely used in all applications, starting from IoT, then even in bioinformatics, even in any sort of data, time series data, and everything. Everywhere it is used. Sorry, there is a mistake. It is BIRCH, balance iterative reducing and clustering using hierarchies. It is actually uses CF tree and incrementally adjust the quality of subclusters. Whereas the other algorithm is CURE, which is clustering using representatives. Okay, it actually selects well scattered points from the cluster and then shrinks them towards the center of the cluster by a specified fraction. Birch is actually incremental, hierarchical, and one scan. So it is very efficient. It actually saves clustering information in a tree. So each entry in the tree contains information about one cluster. New nodes inserted in closest entry in the tree. Uh, Clustering feature used is very simple. You can see that N, LS, and SS. So these vectors are N is number of points in clusters, LS is sum of the points in the clusters, and SS is sum of the squares of the points in cluster. This N is something that you can see that if you have clusters, say 1, 2, 3, 4, 5, you have 5 points, then some of, number of the points will be 5, then some of the points in the cluster, say individual values will be added, and then the sum of the squares of the points of the cluster, and that becomes actually the clustering feature. So balanced search tree will be created, and subcluster has a maximum diameter. This is actually what a balanced birch tree looks like. These are actually CFs of this. You can see that this is your root, and then each root is having multiple CFs which correspond to the childs. Say this is child 1, then child 2. Now the question is how these CFs are actually calculated. As I told you that CF is N, LS, and SS. So three values are there. So when I say that what is the CF1 here? So it is actually the cumulative CF of this. What is CF of this? Then it is cumulative CF of this. And how this CF is calculated is this. This is the cluster which leaf node is having. And at leaf node, you can apply any algorithm. It can be k-means or PAM or any algorithms you can apply. And this CF is generated. So this NLSS will be generated here through this cluster. And similarly, there are this, and there are this, and there are this. So these CFs will be calculated. Now CFs are available. Now this CF will be contributing and is responsible for generating this CF1. How? Certainly, if I say that 6, say 25 or say 89, suppose this is coming, and suppose there are another CF is 7, say 49, say 111, something like this, then these two will be added, these two will be added, and these two will be added, and it will actually generate these two can contribute, uh, uh, sorry, so this, sorry, okay, I don't know, there is some problem. Say, these two will be added, and then it will actually generate the CF1 of the previous node. And similarly, all the CFs will be actually added, and it will be actually cumulative CF of this will be there. There are two constants in this case, that maximum number of CF in leaf node is actually threshold by B, and L maximum number of CF in leaf node is there. That is. Now, the question is that uh, uh,
Uh, uh,
yeah, yeah.
See,
Tell
I
me.
request all the participants to switch off their camera. Miss Sakshi, your video camera is on. Ma'am, please switch off your camera. Sir, you please continue, sir. Sorry to interrupt, sir.
Okay. Okay, fine. So what is happening in this case is that suppose why I am saying that this algorithm is incremental in nature. Suppose a data comes, say D25 comes. Now this need to be inserted in this particular structure. Now insertion and everything is dependent on what is this data and how close this data is with reference to the all the clusters. Suppose that this data is very close to this data, but all the you can say slots are full for this particular cluster. Now the question is then how to feed this particular data in this cluster. So what will happen is that we compare this D25 with all the points of this cluster, and the maximum distance point actually at the mean of this cluster, and the maximum distance from mean data points will be shifted to the sibling nodes or maybe the next node, whatever is applicable. So that happens, and then D25 will be inserted out here. The moment you insert D25 at this in this cluster, then always remember that this CF will change, then this CF will change, and this CF will change, because the number of points will be same, but now the sum of the points will change and some of the squares point will change, and similarly this. So this from bottom to top, this CF will be updated. But the beauty of this structure is it can accommodate any data, any number of data, wherever it is relevant. So the data will be inserted in the same cluster where it is to be relevant. So that is what we have. Effectiveness of this algorithm is very important. That it scales linearly and it has complexity of order of n. Only the thing is that it handles only numeric data, and it actually is sensitive to the order of the data records, because as I told you that at the leaf node, insertion depends on that how data is close to the particular cluster. because we put the data into order form so that insertion becomes easy. The data which is far from mean will always shift to the other nodes also. So that is what we have. Next is cure, which is clustering using representatives. This is very easy going algorithm. For example, what is happening here is that we have sample of data, say the first figure A, then you can have three clusters out of, you can see that in previous cases uh, we only consider the single mean or medioids and all. Here you can say that we are actually the clusters are represented with multiple points. So that is very important in this case. And obviously, depending upon this point, all these points of one cluster and other clusters, so this distance between these 2 points is below the threshold which we are looking for. Then it is always good that you can actually merge these two into one. And obviously you can investigate with these points to these points distances, and if it is actually beyond threshold, then it can be still be the two clusters. If it is within the threshold, then it can becomes a one cluster also. That is happening. Obviously we always look for whenever you look for shrinking of the clusters, we always look for the gravity center by fraction of alpha. So we just check the two cluster distance by alpha points, by alpha distance. It is the algorithm is very simple. Partition the samples into p partition, then partially cluster the points in each partition, remove outliers based on size of clusters, and then completely cluster all data points in sample. And similarly, whatever cluster features you are getting, then it can be all those remaining c points, all remaining points can be mapped to all those clusters. So this is what sample based. It is order of n again. It is very one scan. When I say one scan means just uh, scan is very important for any algorithm. But suppose your data is huge and it is actually when I say that say you have say your size is n and your RAM is say R, size of RAM is R, then what is n by R? When I say n by R, that means it will give you that how many times the data may be called to read the entire data set for once. So that is what number of scans we look for. So what it says is that just reading the entire data at one time can actually be sufficient to execute this particular algorithm. If you go for multiple scans, then it becomes complex and the algorithm may not be efficient enough. So that is what we mean it. Now I'm just moving to the last one, which is very much is density-based clustering methods. Uh, and obviously, there are several interesting studies has been carried out. Say optics, then Denclu, then Click, and all. All these are actually outcome of the research work. References are there. You can always refer to those papers. I'm just going to tell you about DBScan. Density-based spatial clustering for of application with noise. This is what we have. There are two important things which comes in this, that minimum points and epsilon distance. So these two are user defined. So user need to define, and obviously the whole clustering accuracy always depends on how wisely you have defined this minimum points and epsilon distance. So always optimize this to value. There are preliminaries for this particular algorithm. You can see that the first says that it is actually a distance measure is defined on database, and the distance between any point PQ, say I'm just looking for PQ 2 points, is denoted by distance between PQ. The epsilon neighborhood of P denoted by epsilon n BHDP is a subset of dB such that distance PQ is epsilon for any Q belongs to epsilon neighborhood of P. What I mean is that suppose what I see is, say this is P and this is what a Q, these 2 points. Say you take P and go for epsilon point distance, and then having this circle. This Q actually falls under this circle. That means P is within the epsilon distance of Q. Okay, so that is what we, so Q will be referred as neighborhood of P. That is what we mean it. Certainly you can view this with this, that epsilon neighborhood is always referred as that you take any random point P, then go for epsilon distance. This is obviously epsilon distance defined by you. It can take like any unit. I can say 2, I can take, and minimum points I'm taking 4. So if it is epsilon distance 2 going for, and this whatever reason you are defining, it has more than 4 points or 4 points, then this is your initial cluster, or we referred as core point also. So that is what we mean it. So you can see that if the number of points within epsilon neighborhood of P is greater than or equals to minimum points, then P is called a core point. And this first core point is actually a first level of clusters you are getting it. Now, given PQ, which is from database or data, any sort of, it may be IoT data or some data, if Q is actually belonging to the epsilon node of P and P is a core point, then we say that Q is directly density reachable from P. That is what we, and now you can actually go for this, that given PQ, which is from database, Q is density reachable from P if there is a sequence of points, say P1, P2, Pn, such that P equals to P1 and Q equals to Pn, then each Pi plus 1 is directly reachable from Pi. Uh, this can you visualize with this example. Uh, you can see that, sorry, this is, you can see this is B1 and this is B2. So this is my P and Q. Now what I'm saying is I'm going for epsilon distance, say this, and I'm going for the points, and I found that, say this point is within the epsilon distance. Now I'm going with reference of this, I look that this is epsilon distance, this also within the epsilon distance. Then I'm moving forward epsilon distance, and this is also within the epsilon distance. Then this, and this. So all that whatever points which is falling within this distance is actually directly density reachable, and your clusters will be of this type. So arbitrary shape of clusters will be formed, this, and all the points which is falling within this region is your cluster points of cluster. The moment it stops, like no other points are neighbors, then we move to the arbitrary to the next point, and then again the same process will go. That is what DBscan talks about. Okay, it actually creates clusters with order of n square. Then it can like you can reduce it to n log n using a spatial indexing also. Very simple, arbitrary select a point P, retrieve all points, and same process, if P is a core point, a cluster is formed. Then always look for investigate border points, and then move forward to have directly reachable, directly density reachable points, and so on. And likewise, clusters can be formed. And it has the beauty of generating the arbitrary shape of clusters. That is what we mean. Now, this is one thing which is actually a parallel DBscan processing unit, where actually what we are looking for is that uh, you have multiple systems where actually data is distributed or partitioned. Now, each of these systems are actually executing this DB scan. Now, the question is that each of these partitions will generate their own clusters. Then the question is how to have a global clusters out of it. That means, say, what I'm saying is that this is, say, terminal 1, terminal 2, and terminal 3 applies DV scan and all. So each of these will have their own set of clusters, like this, suppose. Okay. Now the question is that how to merge these clusters to get, say, global clusters. It may be 3 or 4 or maybe like that. Okay. Or maybe 5 also. It can generate. Now the question is merging of this, because you look for global clusters. How it works? So this actually, you have is, what we do is we consider this, say, this cluster, this particular cluster, say P, and this cluster, say Q. So I'll consider this as PU and U, and what we are saying is that this is the one cluster and this is the another cluster. This is what we have. Okay. So I'm just doing one thing, that I think I'm taking a bit more time. I think just have patience. What we do is that you can see that what we are defining here is this. What we are defining is this is outer region and this is inner region. This distance is epsilon, and again this distance is epsilon. What we are doing, that with epsilon distance we are creating an inner region and outer region. This is by, say, cluster 1 of terminal 1, and say this is cluster 3 of terminal 2. I'm just investigating that whether there is a possibility that these two clusters can be merged or not. Now, outer region and inner region we have defined. Now, there is a possibility that there is a point P which falls in the common region of the point, because what we have, this is the boundary of these two clusters, and this is my epsilon distance and this is my epsilon distance. So the outer region of this particular clusters will fall here, and outer region of these clusters will fall in here. So these are the common regions which we look for, and this is Px. Then, considering this point, go for epsilon distance and then move this. If the points of this clusters and also of this cluster falls in this particular region, then certainly these two clusters can be merged as global clusters. So the C1 and C3 will be merged. If the points are, like, suppose there are no such points from this region and this region falling within this, then certainly you cannot merge. So inner region will have certain set of points with reference to this particular common points which is having from two clusters. So this way you can generate global clusters, and certainly the same algorithms can be processed on parallelly on different set of systems. So certainly what I mean is that a set of systems you can take, you can create a cluster of systems, you can distribute and partition the data into on different systems, and locally, based on the local available data, you can apply the algorithm, and the algorithm DVScan can generate their own set of clusters. And now the responsibility of one coordinator system is to merge these clusters, and at that particular coordinator this process will carry out. And similarly, each of the clusters, with each of the clusters of the other terminals will be investigated, and based on this property it can be merged or it cannot be merged. So depending upon what sort of clusters can be merged and what sort of clusters cannot be merged, the number of clusters will be generated finally for you, and that will reflect the entire data set. So that is what we do it, and it is very effective and all. This is actually the paper where actually presented, and it actually talks about parallel processing of DV scan. Uh, this is what I was supposed to deliver, and obviously I cannot say that this is what there are so many algorithms available. What I did is that I just picked the important algorithms And giving you the idea that how it works, I have started with characteristics of the IoT data. Then I move to give you the uh, you can say characteristics of big data, then how parallel processing could be done, then clustering, then how data types could be inferred, and then moving forward to some clustering algorithm, which actually is very important and can be used for any sort of applications you might be working on it. There are another set of algorithms which you can go through it. Uh, like I'm always I always welcome if you need my help for any such work or projects if you require. Thank you very much.